Okay, I might start off with a couple of housekeeping things and before we get started. So, and I'm sure some people will still be coming in. But I wanted to start firstly by acknowledging the Ngunnawal and Ngambri people who are the traditional owners of the land on which those of us at ANU are working. And also to mention, we are recording the talk, so it will be put up online, but we just record the talk and not the question and answer session. So question and answer session won't be recorded. In the talk, if you could turn your microphones off, that would be great, but we would ask then if you turn them on and your video, if you can, when we move to the question and answer time, because it makes it a bit more of a discussion even though we're online. So today, as you probably know, it's a great pleasure to introduce Clare McFadden, our speaker for this month's Synapse talk. So Clare is a postdoctoral researcher in biological anthropology at ANU's College of Arts and Social Sciences, and she leads the Centre for Paleodemography and Paleoepidemiology. So a lot of Clare's research focuses on refining and expanding paleodemographic tools. So she's developed methods to use skeletally derived age at death data to estimate past population dynamics, including fertility and maternal mortality and natural population increase. But her research also focuses on ancient Southeast Asia and the Pacific and using understandings of population dynamics and health to reconstruct the human past. Sorry, I'm just admitting people at the same time as talking. And so it's wonderful that today Clare is here to talk to us about paleodemographic advances and potential applications in the Pacific. So I'll just pass on to you, Clare. Thank you.
Thanks, Beth. All right, I'll share my screen. Okay. And just before I get started, I would also like to acknowledge the Ngunnawal and Ngambri people who are the traditional owners of the land which I'm coming to you from today, and pay my respects to elders past and present and emerging. So thank you, Beth, for the introduction. As Beth said, I'm a biological anthropologist, but my primary sort of area of work is in paleodemography. And she's absolutely right in terms of my bio that to date, most of my work in this area has been developing paleodemographic tools and refining those, and then a couple of sort of broad regional applications of those methods. But it's worked out really nicely in terms of delivering this talk. But in the last, I would probably say 6 months or so, I've really sort of taken a very critical eye to my own work and the paleodemographic work that we're still seeing a lot of in that style published at the moment of these sort of big regional studies, and sort of questioning how we can get everyone's microphones off. That would be great. So in terms of the work that I'm doing at the moment is really moving into how we can examine paleodemography in a multidisciplinary model, where I guess, you know, as much as my interest is in paleodemography, the demographic aspect is just one of many aspects of the human narrative, and looking at how we can better integrate it rather than, I guess, using it as this focal point, which we're attaching other things to, which is our sort of common way of doing things, and looking at how we can take a more integrated approach from the get-go. So that's what I'll be talking about today. I have a bit of a map for you of how I'm going to run through these things. First, I'm going to speak about what we sort of broadly consider to be empirical paleodemography. So this is where we're using paleodemographic proxies or archaeological proxies to estimate paleodemographic variables. So there's been some recent advances in this space over the last decade. I'll talk a bit about work in the Pacific, and then I'm going to speak about demographic truisms, I guess, and what I sort of think this empirical work is telling us at the moment, and where I'd like to see it go. I'll then talk about theoretical and interpretive approaches in paleodemography, things that we're doing at the moment, some of the issues with that, and then I'll talk about moving forwards where I sort of see this going in terms of finding a bit of a balance. I'll talk about a new model for understanding past population dynamics, and finally I'll talk about how I see applications in the Pacific region going forwards. So starting with empirical paleodemography and advances in this space, just for those who aren't familiar with the area, empirical paleodemography uses archaeological proxies to estimate or approximate population dynamics. Now, most of this has been in terms of population growth and population increase. There have been estimates of population size as well. But as I'm speaking about advances in this area, the focus in the last sort of decade or so has really been strongly on growth and increase and decline. So any sort of trajectory of population growth, whether it's negative, stable, or positive. And there's two common types of proxies that are used currently. Now, these are the density or the frequency of radiocarbon dates, and these are analysed through a few different statistical models, but in essence, they're plotting the volume or the frequency or density of radiocarbon dates across a temporal distribution. And what we might expect to see is that if a population is increasing in size or more active, or there's more active members of the population, we may see more material culture producing more radiocarbon, or more carbon to be analysed. So the frequency of radiocarbon dates is then interpreted in these models as being indicative on a relative scale of what's happening with populations. So if we see a sudden decrease in the density of dates, then that's considered indicative of decrease in population growth. We then also have the representation of kids or sub-adults in the age at death distribution. This is the area that I have been based in for some time. And this looks at the process of examining human skeletal remains, estimating age for the individuals in a burial sample, and then looking at the proportion of children in that sample. And the proportion of children can tell us, again, whether the population is growing or would likely be declining. And this is sort of based on, the work that I've done has been based on using United Nations data, population data, to look at how the representation of children in the age at death distribution can be a predictor of population growth, also of fertility rate. So those proxies are giving us an approximation of what we think population dynamics in the past really looked like. And both of these proxies have been used for quite some time. They've got 3+ decades of use. But recently, there's been quite a lot of work done on both, the skeletal side mostly by myself, and the dates as data or the radiocarbon dating analysis by several eminent scholars in the area. So first I'm just going to talk a bit about these radiocarbon date approaches. One of the great things about these is they make really good use of existing data sets, and there are some pretty massive data sets of radiocarbon dates available. So they can use these existing data sets, they can accommodate new data as it becomes available. And in the past, I guess one of the primary concerns with using this approach was Tethanomic bias and other sources of bias, which may mean that the density of radiocarbon dates, which belongs to any particular point in time, they refer to these as bins, partly because of the accuracy of radiocarbon dating, and partly by virtue of how the method works, you need to have bins to put these dates into. And the bins can vary in size quite substantially. There's some studies that use sort of 50-year bins, there's studies that use 500-year bins. It really depends on the research question. But sources of bias may end up with dates being in the wrong bin or the bin not being representative of that particular time bracket. So taphonomic bias is one of the obvious ones that comes to mind. The fact that things may be less well preserved as we go further back in time. There's corrections for this, mathematical corrections for this. They use a lot of looking at volcanoes and geological sources of information to inform these corrections. So some of them are like a little bit on the sketchy side, I guess, but these are definitely improving. And there have been some really great taphonomic corrections that have been coming out, particularly regional corrections. So there's region-specific taphonomic corrections available to assist with that. So I guess in application, what this looks like is we might expect that due to taphonomy, we may have less radiocarbon dates in the deep past, and these corrections will account for that. We have random error and other sources of bias, which are somewhat addressed through the statistical approaches that are being used now. So moving forwards from, you know, the sort of like early 70s when these methods were sort of first kicking off, we now have sort of Bayesian approaches incorporated into it. We also have Monte Carlo simulations applied, which is where variables are changed incrementally by small amounts to sort of see what things look like if we have a little bit of error occurring. And in the picture that I have here, or the graph here from RIRIS 2018, which is one of these studies applied to Peruvian samples, the grey highlighted area is the Monte Carlo simulations. I think you ran about 1,000 Monte Carlo simulations. So it sort of gives us a confidence interval of where we think this trend line fits. Good things about this approach include that it's got accessible software for doing these sorts of analyses. These are packages typically available in R. And so more or less anyone who has access to or has their own database of radiocarbon dates is able to use this method. So it's quite accessible. One of the bad things about it is it doesn't really tell us much about population processes. So it gives us a proxy for fluctuating, I guess, population activity. It's not so much a direct proxy for, you know, the rate of natural population increase, which is births minus deaths, or total fertility rate. So as a demographic variable, I guess it could be considered capturing some different population processes all at once. And the scale of measurement is way off in terms of how we interpret this. I'll talk more about it a bit later. But what's really interesting is all of these studies are producing these estimates of population growth that are like 0.04%. And we know from modern populations, from ethnographic studies of small communities, but even at, you know, the large scale population level, at the national level, populations tend to grow somewhere between 0 and 4% rather than 0 and 0.04%. So these are really sort of crazy low population growth rates that are being estimated from this particular method. So, I mean, it doesn't mean that the trends are incorrect. The trends seem to be overwhelmingly, they do seem to be correct, but just the scale doesn't quite match up. And this has been subject of some recent discussion in issue in Royal Transactions B, philosophical transactions B, on cross-disciplinary approaches in paleodemography. So turning to the skeletal side of things, which is the sort of stuff that I have done in the past. Again, this makes really good use of existing data, osteological data and burial data. In this approach, rather than trying to correct for bias, we pretty much just exclude samples that we're quite sure have biases in them. So if it's only males and it looks like it's a military burial or something like that, we're not going to try and estimate the population growth rate from that. Equally, if we have no children, that sort of removes our means of doing so, and it would seem silly to try in the absence of that, because it doesn't seem to be a representative population. But having said this, the new tools which I've developed over the last few years have really quite a good tolerance for error. So we did some testing of them in various scenarios. We didn't run Monte Carlo simulations on this. I've always sort of opted or tended in the past towards sort of simpler approaches to error testing in scenarios, like on a scenario basis, but certainly Monte Carlo simulations would probably be useful in this space, but they do seem to have really good tolerance for error, which means if there is some sort of Tethanomic bias occurring, I think most of the methods performed pretty well up to somewhere between 25 and 50% sort of anticipated Tethanomic bias, I guess. Simple, accessible equations, not dissimilar to the dates as data approaches. I don't have an R package for this yet, but some colleagues of mine in Germany have developed one for me. And they've also put some other measures in there too, which is amazing. So they do have a package in R, which data can be dropped straight into. I also have an online calculator, which is an Excel spreadsheet plugin for the website. In this case, our dating bins, and I mentioned for the radiocarbon dates, the dating bins is sort of usually 50 to 500 years. For osteological samples, often our dating bins are a lot bigger because we may be using sort of bracket radiocarbon dates for the burial. And so the burial usage may, based on those dates, appear to span, 1,000 years or more. This is probably one of the biggest things that we sort of grapple with is in this, which is from one of my papers on population growth in Southeast Asia. Most of these data points, because they've been averaged, they could really sit, most of them, anywhere between sort of 250 years either side of where they sit in this graph. So for some of them, that's not particularly going to be, matter. But if somewhere like Ban Wat moved forwards 500 years, that would definitely influence the trend that we're observing here. So the dating bins, there are some concerns about in this area. But in terms of advantages, through these methods, we can accommodate single population analyses, which is a really nice thing. Radiocarbon dates, because you're looking at relative change in the frequency and the density of radiocarbon dates, you basically need a minimum of 2 points to look between the points and see how things are changing. This proxy for the skeletal analyses allows you to just look at a single population. So you don't necessarily need a local reference point or a reference point for that same population. Obviously, most of our research questions are going to be focused around some sort of change. So we will want those things for the sake of the research question, but I guess for the sake of the method, it's not a requirement to have multiple data points. In terms of the scale, the way the method's been developed ensures that the scale is where we want it to be. So the estimates are pretty representative in terms of scale. On the side there, I've got just an image from one of the articles in the in that cross-disciplinary demography issue that I mentioned, and this shows the difference between ethnographic estimates of population growth rate. I think they define this as for hunter-gatherer or hunter-forager populations, and the archaeological estimates. And I would say this is sort of a best case scenario, really, because we've seen, yeah, a much greater polarization, I guess, in some cases as well. But this is the archaeological samples they're talking about here are the dates as data approaches. Our osteological analyses, and in that previous slide I showed, this is rate of natural population increase. You can see that the scale that it's on, so 1%, 2%, 3% growth, is much more in line with what we'd expect to see based on ethnographic counts. So in terms of the forager population paradox, which is the archaeological estimates of growth are orders of magnitude smaller than ethnographic and historical estimates, we've gone some ways in addressing that, at least through this particular methodology. We do have the persistent issue, though, of averaging on the temporal basis of averaging over the burial use span of time, which is probably one of our main things. There's probably some opportunities to address this through time series analysis in the future. So what are we getting out of this? Sorry, I'm just moving my camera thing around because it keeps going over the top of my screen. So what are we getting out of these sort of empirical studies? Well, the findings that we have are broadly pretty similar, and we actually have pretty similar issues that are coming out for both. Some of this is to do with the accuracy or the representativeness of these proxies. If we're using proxies, we want the proxies to be representative of what things look like in real life. So if the material, the archaeological material, whether it's radiocarbon dates or whether it's skeletal remains, are not accurately representing that, then we obviously have an issue, and there's still some concerns around that in both cases. The precision and the accuracy of the dates is also still problematic. We have had improvements in this space, I guess, but particularly for osteological samples, we can end up with quite large bins for dates, which means that things could move pretty substantially in terms of trends. And for dates as data, there have been concerns raised in sort of more specific cases about the accuracy of radiocarbon dates, or cherry picking of dates as well has been raised as one of the concerns. We also have to think about the precision of the statistical analyses that we're using and their ability to accommodate error. And as I said, I think we've had some really good advances in this space so far, but there's probably more that we can do as well. So I think there's more advances to come. But in spite of all of this, all of these sort of diverse things that we think may be causing or could be contributing error, we find broadly consistent results. And this example from Downey et al. 2014 is a comparison of proxies from the radiocarbon dates, which is the image here, and from the skeletal remains, which is the top image here. And I've just lined them up. The scales are quite different, and we would expect to see a little bit of a difference in the shape of these curves. Sorry, the garbage truck's just going behind me. But broadly, we can say that the shape of these curves, and once we have some correction for the different scale that they're on and the different types of things that they're analysing, that broadly the shape of these two is quite similar. The top graph goes a bit further in terms of dates, but yeah, we can see that they're quite similar in shape. So we're getting some sort of what appears to be cross-validation by looking at these two proxies. And, you know, what we can learn from this, we end up, this is a lowest fitting procedure, which I'll talk a bit about later, but it's sort of a bit of a kind of approach in statistics to identifying trends. And we can see that we've got a lot of outliers, or, you know, what we typically sort of consider outliers from a statistical perspective. We've got several data points that sit well and truly outside of this 95% confidence interval. And it looks like around these trends, we're getting like quite a lot of noise. So is this bias in, you know, to taphonomy or various other sources of introduced bias? Or is this genuine variability in how populations are behaving? And when we look at these sort of broad regional studies, I mean, this is Neolithic Europe broadly that is pictured here. Why are we expecting to see this incredibly high degree of conformity in population trends? Why would we be looking for these really tight population processes that mean that all populations across, you know, massive regions and huge periods of time are responding in the same way to often singular events? I mean, this is looking at pre and post agriculture. So, you know, our research questions are based around this assumption that we're going to see a consistent population response to certain events. But I think what's really interesting is what's going on with these outliers. So I'll talk a bit now about work in the Pacific, including some of my own work. This is an area that I'm quite interested in, and hopefully audience members are as well. So studies in the Pacific region in terms of population dynamics in the deep past have sort of tapered off in recent years. We've seen some pretty incredible historical demography from people like Norman MacArthur and others, and the Kirchin-Ralu volume on growth and collapse in the Pacific covered quite a lot of settlement approaches to paleodemography. They note the concerns with this and some of the issues with this, but the reason that I'm not going to go too much into the settlement approaches to paleodemography is because I guess my background hasn't been specifically in the Pacific. I've been sort of more in the methods development space, and the Pacific is really the main region that we still see this type of settlement paleodemography used. It's not used much elsewhere in the world, and particularly not in recent years. So in terms of, I guess, different methods in different regions, we've just seen that, you know, while a lot of the methodological development has been in other methods, they're methods that aren't commonly used in the Pacific region. That's not to discount the settlement demography that's been done. It's just sort of different approaches in different areas, I guess. And as I said, they do note some of the concerns with this differential use of settlements and structures, as well as the reuse of settlements and structures may sort of contribute to some errors in estimates of population size on the basis of settlement demography. There has been some dates as data work done in the Hawaiian Islands, the Society Islands, and in Micronesia. This example from the Society Islands is, as I said before, there's been a suite of statistical approaches introduced looking at radiocarbon dates. This is sort of the raw approach to doing so. And I picked these two out I mean, partly because I put them side by side, I should say. I didn't cherry pick them out. I put them side by side because they're just so strikingly similar. I was pretty astonished when I sort of stumbled across that. For the Hawaiian samples on the left and then the Micronesian sample on the right, you can see in terms of dates, I mean, they're on a slightly different date scale at the bottom, but just like absolutely strikingly similar distributions that we're seeing. And this is pretty common. I mean, as I said, for the European study, you look at this entire European region and you get similar trends, very similar trends, for radiocarbon dates and osteological analyses of population growth. Those trends are quite similar in different regions of the world when we look at how things sort of happen over time. And then here again, we're seeing these strikingly similar trends in different locations, again, over a sort of similar period of time. More recently, in the last sort of few years, Rapa Nui continues to have a whole lot of research into population dynamics published on it, still quite contentious over whether it's this ecological catastrophe or ecocide, much slower and less dramatic sort of population decline, or whether the population was growing and it's genocide with European contact. So we have different models emerging for this, and it's still quite contentious. This article that came out last year sort of looks at whether all of these are mutually exclusive models or whether you can have an interplay of these factors, which is quite nice. And looking to the osteological analyses, we've got some from, I mean, there hasn't really been anything done aside from my work, which I'll talk about in a moment, since sort of these in terms of actual analyses in this space. But there has been some, pretty large samples examined. There was the work by Snow, which is 1,174 individuals in that collection, which has since been repatriated. And then work by Kurt as well in his 1984 volume on the Polynesian chieftains. There was critique of pretty much all the paleodemographic work that had been done today at that time in the Sutton and Malloy article, and also by Brewis a few years later. But they basically, in both articles, the concerns raised with paleodemographic studies in the Pacific to date were that they were basically showing confirmation bias, with people leading into this research expecting to find carrying capacity being the major, I guess the major definitive sort of factor in population processes in the Pacific. The idea that on an island, you have more limited resources, and so carrying capacity is capped at sort of a particular point, and then the population growth rate tapers off. So this, amongst other sort of demographic theory, Malthusian theory, were considered to be sort of assumptions that were made that were problematic when these studies were undertaken. There were also concerns about inaccurate methodologies that were used, which was seen to more or less undermine some of this paleodemographic work. All right, turning to my work in this area, we sort of set out, I was in my PhD when I did this work, and developing these new methods of looking at population growth from skeletal remains. And when we set out doing this study, we sort of had to come up with a broad idea of what we were looking for, as anyone does. And we sort of said, okay, well, maybe populations respond to local environmental conditions in a similar way. So maybe what we want to look at is how populations respond from as sort of a relative temporal process from when they arrive in a new environment or on a new island, new archipelago, and look at those sort of changes on that time basis in contrast to absolute time. And the second hypothesis that we were looking at was whether populations respond on absolute time, which would suggest it's sort of something broader in the region. It's to do with climate or sort of major events that impact everywhere at the same time. We did fortunately note that these two hypotheses are not mutually exclusive. But I think revisiting this now, it was already like a little bit problematic in terms of we've narrowed down these sort of possible ways that populations respond. We've sort of broadly categorized them into they either respond at a local level on a relative temporal scale, or they respond to across absolute time to these sort of major things. And while we sort of said not mutually exclusive, the way we've tested it is to look at them separately. Just quickly, these are the samples that we included. I just thought I'd pop them up there for anyone who's particularly interested in the Pacific region, so you've got a bit of an idea of where we are. Got a line on there. So this was our sort of plot of how these populations or how the population processes were occurring. This is the temporal distribution based on time since earliest known occupation for each of these archipelagos or islands. So it's plotting them on relative time. And I guess the idea that inspired this was a lot of the work by Palaeodemographic on the Neolithic demographic transition, and noting that this sort of event of agriculture happens at different points in time in different places. Everything's sort of zeroed out to that. So if we think that there's some sort of process of adaptation occurring as populations arrive in new spaces, we need to, in a similar way, zero it out to time since they've arrived in a new place. Now, there's obviously a lot of assumptions in this, and as I've sort of got a lot more familiar with both the Pacific region and I guess the population processes that we're trying to model here, there are quite a lot of assumptions in it. But what we do see is this somewhat of a trend, it would seem. I'm not sort of too concerned about what happens over here, but what we sort of thought we were identifying is this process of populations with quite a high growth rate for the size of these populations, and then it sort of tapers off. Now, it's not declining. The population growth rate is still in the positive. We're still above zero. So it's just leveling off. And I think coming back to it, I'm probably jumping ahead a bit here, but I suspect this is one of these demographic truisms that I was talking about. That what we're actually seeing here is when you, as sort of setting up a new population in a new place, you are going to have a high growth rate because you're not going to send out, young children and the elderly. You're going to send out people in childbearing age groups. So I suspect this is just essentially a truism rather than sort of an adaptive resilience process. I think what we're seeing, because we just don't have enough data points to say anything with any confidence about what's going on here. I suspect what's going on at this end is purely that we have populations with good capacity for growth populating new areas, which to me would seem like a bit of a truism. On this temporal distribution, so this is absolute time, things get a bit more chaotic. I can't remember the exact value for this polynomial trend, but it wasn't very good. And what we can see is we've got populations sort of sitting a bit all over the place. But it brings me back to what I was saying earlier, is why are we expecting to see this really consistent population trend? I mean, populations respond to so many different variables, and they respond in different ways in different contexts, you know. So as soon as the conditions change slightly, those responses can change in sort of a hierarchical way. So why are we expecting to see these sort of glamorous nature paper style population trends where everyone conforms and sits nicely around the trend line, when we know that these responses are just so diverse and there's so many different things that can influence them? So in our conclusions in this paper, we say high population growth at the time of and immediately following colonization was observed for the majority of islands and archipelagos. Then there seems to be somewhat of a decline in growth. Again, I think this wording I need to be really careful with, because it's not a decline in growth rate, it's just a slowing of the growth rate. And then it looks like they generally sort of began to increase again up until European contact, although we saw that it was pretty messy at that end. And we concluded that both trends support the assertion that at the time of European contact, island populations were in different stages of demographic oscillation. So we have these sort of similar trends appearing all around the world of increasing growth over time. And in this case, we see some possible sort of disruption and variability pre-European contact. Things look a bit more all over the place. It does look like the osteological and radiocarbon proxies seem to align. So those radiocarbon plots that I showed you before, they align incredibly well with each other, strikingly well with each other. But the osteological work that I've done recently, which honestly in terms of narrative does not differ that significantly from earlier work where methodology was the concern. Even with the new methods, we seem to be getting pretty similar things coming out of this. So things seem to be aligning, but these sort of overall trends and these big regional analyses, and it's very much true of my work in this space, they can be of interest to big questions, but I think the more localized studies have even greater potential to contribute to those questions. The broad studies, in terms of, and I always wonder whether I should talk about this at the start of my talks, but you know, what are we talking about when we're talking about populations? Because we're talking about population dynamics of the Pacific region in this this recent paper, and it's like, well, I mean, that's just huge. That's not a population. You're not dealing with a population. You're dealing with a whole, you know, array of populations, and not only through space but also through time. I mean, you're dealing with what many people would consider just a huge volume of discrete populations. So what are we actually learning about populations or a population from these sorts of studies? One of the points that I've used to encourage people to take up these sort of osteological approaches to paleodemography is that it gives us the ability to put the individual back into the population in a way that the radiocarbon data approaches cannot. But I think I'm guilty of the same thing, that, you know, it's time to put these individual populations back into their regions rather than just sort of sweeping over entire regional analyses. We really need to be looking at what's happening with individual populations because that's where I think it's interesting and exciting. So in terms of demographic truisms, sort of started on my rant about these already a bit, but many of these studies treat population dynamics as the focus point or the primary variable, and everything else around it is built around as explanatory sort of variables, explanatory adjuncts to the population dynamics that we're looking at. Sometimes we hinge the population dynamics on a particular event, like introduction of agriculture or intensification of agriculture. But generally these other variables are sort of treated in a supplementary way, or they're treated as a pivot point. And we know with agriculture that this isn't true either, that agriculture is not a linear process. Some populations or communities pick it up and then they drop it and then they come back to it. So how do we accommodate that in these sort of models where we treat things as pivot points or as sort of supplementary things? And often what we do is we do it in quite a qualitative way, that we contextualize what we're seeing based on these things, these other variables that we're aware of what's going on with them, which again seems to be very much a confirmation bias risk. So these significant regional analyses really don't tell us a lot about a population and what can we really expect to learn from these sorts of approaches. This is another example of the lowest fitting procedure, which has been applied here to the introduction of agriculture, which is 0.0. And we can see here again, we're getting this thing of, you know, okay, well, yeah, you can bang a trend line on it. But there's just so much, you know, what, as I said before, we'd sort of call noise from a statistical perspective, but I think this is just the true story of these populations. It's just that we're trying to get some sort of clear trend out of it when there probably isn't one. I think this is a really good example of some of the issues and how we're interpreting these things. So this is from a paper that was in PNAS in 2016, which looked at similar data to this previous one actually, but from radiocarbon date perspective, looking at the impacts of agriculture on the annual average, and it doesn't have it listed here, but there should be annual average growth rate. And they said the human population worldwide appears to have grown at a constant annual rate of 0.04% for most of the Holocene. Now, this is problematic from a few different perspectives. The work that they've actually done is really good. The data that they've used, there's nothing wrong with, but it's the interpretations in this that are problematic. Now, what's displayed here, these are author names for other studies, and shows the range in average annual growth rate that were reported in each of those studies. Again, for substantial regions or substantial regional analyses. So, you know, North America, Europe, the UK, these sort of really broad things. And we can see the annual growth rate that's been reported for all of these falls somewhere between 0.02 and 0.08%. And as I mentioned before, we'd be expecting to see something more like between 0 and 4%. So they're all sitting very low. And then they say the same rates of prehistoric population growth measured worldwide suggest that the global climate or biological factors intrinsic to the species, rather than factors related to regional environment or subsistence practices, regulated the growth of the human population for most of the last 12,000 years. This is the main chart, which shows, so SPD is summed probability distribution. So this is the distribution of the radiocarbon dates once converted through the particular statistical approach that they've used, and use BP at the bottom here. But what's interesting, I think, is like, okay, you sort of calculated your across your average of, you know, somewhere about 0.04 across this line. But I mean, look at the either side of it, like what's going on. You've got so many peaks and troughs occurring, which is exactly what we'd expect to see in sort of an oscillating population model. You know, you could have like a particularly good season and lots of resources and things are warm and lovely and everyone's doing great. And so more babies are born and population's growing. And then you might have, you know, famine, you might have a catastrophe, you could have anything, you know, epidemics, whatever. And we see population crashes, and that's what we'd expect to see, remembering that this is over a huge period of time. So I think this tendency that we have to focus on what's happening in terms of this particular line, rather than looking at like, what are these? Like, what is going on here? I think is really problematic. And I think what we're finding is these demographic truisms that, you know, populations do oscillate and they do regulate. And we know that populations can't have grown constantly at a high level. When we average it, they do have to grow at these really low rates, but we're averaging over thousands of years. So the amount of variability that you're flattening in that averaging process is just huge. And I think it's just not particularly of interest to say that, you know, populations over really, really long periods of time grew at really low rates, because we sort of know that just by how the world is now. So there's not sort of anything really interesting to me in looking at those sort of really long-term, really massive region analyses, looking for these really cohesive trends. What's interesting is the variability and the fluctuations. And to start to understand that, we need to have a look at localized studies, because we can't capture that as an entire region over, you know, a 10,000 year analysis. So this work by Talavera and Jorgensen, they argue that the problem is the precision of the methods, and that's that this schematic over here, which shows sort of the different scales of demographic processes. They say it's an issue of the precision of the methods, and I don't totally disagree. I think the precision is part of it, but I think a huge part of it is the interpretations and the interpretive models that we're putting these data into. So these broad regional analyses just tell us the same thing time and time again. They're just telling us these demographic truisms. And I think this is typically, out of these big analyses, it's really the only thing that we can say with any certainty, because we don't have the resolution in the regional analyses to drill down into what's going on at these lower levels. So returning to my own work on the Pacific, you know, it even reads, rereading it, as very much, you know, demographic truisms. Populations with good capacity for growth colonized the islands. It's sort of like, well, duh. There would have been processes of adaptation in terms of diet, subsistence strategy, adapting to the landscape. And adverse conditions, as well as favorable ones, could cause peaks and troughs on a smaller scale. I mean, it is very much stuff that you sort of go, well, yeah, like it makes sense. But how are we going to investigate this? Because at the moment, these massive regional long-term analyses are not really doing much for us. So why do we expect to see these patterns? Smaller populations are more demographically volatile than large ones. So I think that's definitely something we should be keeping in mind. And I think these outliers, or, you know, the fluctuations, which are often treated as outliers, are really the opportunity for us to tell population-specific stories and contribute to a better understanding of population dynamics. The tendency to assume that they're outliers, I think, is probably wrong. I think a lot of these are quite representative. They're just showing the diversity and variability of population responses to their conditions. So I think these data in isolation tell us very little about how populations operate and the processes that they go through. I think their findings are only really meaningful in a multidisciplinary model, but I don't think we necessarily need to have paleodemography, even as a paleodemographer. I don't think we need it to be sort of the center focal point for any of these studies. It's just a facet of human experience and the human narrative. So multidisciplinary and multivariate models is, I think, where we need to go with this. Okay. So what are the approaches that we're using in interpreting these data at the moment? We've got quantitative approaches in paleodemography. Some of this includes iterative simulations that change the scale of the parameters included. So when we're looking at populations, some of the typical things that we see are environmental things. So the temperature, you know, mean annual temperature, mean annual precipitation, and things that are expected to influence the availability of resources. So some of these simulations will look at how do we think populations respond, or how do they appear to respond when we make small changes to these parameters. I mean, it's a good way for accommodating for some of the inherent error in measuring these things in the deep past and dealing with archaeological sources of evidence. Monte Carlo simulations are used for this for radiocarbon dates. And then we have things like agent-based models, which sort of do a combination of these things. But in any case, I would say these quantitative approaches really only tell us how well the included parameters are predicting population dynamics. And in some cases, whether the population is conforming with expectations. And I've got an example of this in terms of agent-based modeling. I've put some highlights in here, but essentially what I'm getting at in terms of the highlights in this quote from this paper by Axtell et al., which looked at population dynamics in Arizona, is it's very environmentally focused. So they've sort of said, you know, this is a really good opportunity for agent-based modeling because we have a whole lot of environmental data to plug into this model. So we already get a sense for the sort of parameters that are going to be included in this agent-based model. And I thought as I was going through this study, I've thought it before, like the last time I looked at it, it's quite similar to that. If anyone's familiar with the old game Oregon, the Oregon Trail, where you have these really sort of fixed resources and quite narrow parameters that determine whether you live or die. And in this case, you know, the nutritional requirements were estimated from ethnographic studies and also some historical studies. And then, as they say here, and from other subsistence agriculturists. And they come up with an idea of, you know, what this population should look like based on these variables. But the data that are put into this are very precise. I mean, so it has things like the nutritional requirements are 130 kilos a year of maize. And we can imagine that there's probably quite a lot of movement around that point. So there was some initial work done, and then there was some later work done, and in the later work, which these quotes are from, there was some adjustments to the scale of different parameters to see if they could get things operating a bit better. But what's really interesting is in this quote here, all attempts to reduce the population in that model by changing agent parameters resulted in premature population collapse. So this is like one of those, to me, one of those sort of classic examples of, you know, we've put all the parameters in, we've estimated them as best we can, and then things just don't work out. And as they change the scale of the parameters that are included, it just keeps failing, and this poor population keeps collapsing in the agent-based model. So I think one of the problems with this is, in the end, in that paper, they sort of try to get towards best fit, but it still has some issues. And I think the problem is, what parameters are we missing from this model? So, you know, you've considered how do we change the scale of the parameters that we've included, but how, you know, are your parameters correct? So what are you missing? What are the variables that haven't been included here? And I think this is problematic with a lot of sort of more strictly quantitative approaches to interpreting paleodemographic data. Often it relies on ordinal data for these sorts of models, and a lot of the data that we're interested, or the variables we're interested in, they just don't work on an ordinal scale. Some are difficult to quantify at all, and others are not ordinal in nature. Often we lack the precision in the archaeological record to reasonably and confidently estimate some of these parameters. So as I said, you know, 120 or 130 kilos of maize being a requirement for an individual, it seems like a pretty difficult thing to estimate to me. So, you know, what are we missing in terms of the parameters? Looking to qualitative approaches, I mentioned before low S models. So low S models sort of give us like it is a statistical method, but it's sort of a semi-qualitative thing. which really allows your data to do all of the wiggling that you might expect it to, particularly when it comes to population processes. But it doesn't really tell us that much. I mean, we're pretty much eyeballing the results. And I've shown a couple of examples of this already, but we have these graphs, these low-S graphs or low-S plots, where the low-S procedure will fit a trend line. That's what it does. But I mean, you look at the number of sites that are around here. The other thing, which I did as well in my Southeast Asian study, but we deliberately drew attention to it, is if we're looking at sort of a before and after trend, as they are here, before and after agriculture, this is North America, osteological analysis, we have significantly less data points on the before side. And you could almost envisage, looking at the after side, that this is more or less a random selection of this like distribution. So whether there's actually any difference between the two, or whether it's just a product of the lack of data available on this side, is pretty contentious, I think. And we have this bit of a habit of ignoring things that don't really fit with the model that we want when we're doing low-S plots. And in this case, this was used as evidence that there was a significant increase in population growth following the introduction or intensification of agriculture. And as I've just said, I think that's pretty dubious, considering the lack of data points on this side, but also just the distribution on both sides. Moving here again. So this from Kohler and Rees, this is looking at the North American Southwest. A plausible interpretation is that populations increased in size in the Southwest for 2,200 years, from no later than 1100 BC to 1100 AD, stabilizing or declining after that time. And again, looking at these plots, I mean, we have somewhat of a trend line, but we've got a substantial number of data points that are sitting well and truly outside of this 95% confidence interval, and setting quite far away from the trend line. So what's going on with these populations? And as I've said a couple of times before now, why are we expecting them to all conform to this really clear pattern? Other qualitative approaches in this area, we get a lot of schematics from demography and ecology, also some from economics, flow charts that look at how demographic processes interact with environment, biology, and culture. When we're borrowing these from other disciplines, one of the issues in the past has been, and probably is now, sorry, I shouldn't say it's just in the past, we sometimes forget to look at, whether these are things that we can actually measure or estimate from the archaeological record. So these maybe, some of these are really, good ways of looking at the relationships between variables. But if we've got no means of actually examining it, then it stays strictly in the theory space. So often these aren't data informed, at least from the archaeological perspective, and they can be difficult to apply. This one is from Hassan, a major paper on Neolithic demographic transition and the variables that contribute to increased population growth following intensification of agriculture. And you can just see from an approach of taking paleodemographic data and the proxies that I've mentioned, to incorporate it into a model like this is just sort of very daunting and perhaps unfeasible. So how do we find the balance in all this? So I think multivariate models are really important to understanding demographic influences and consequences, whether or not the demographic is sort of the primary variable in that doesn't really matter. I think it is important to understanding human narratives. I think it's a very important factor or facet that needs to be included, but it's not necessarily any more important than any other facet. I just think it makes sense to include it in these sort of comprehensive models when we're looking at things. The nice thing about building these, or building some sort of model that has quantitative and qualitative contributions, is it gives us some scope to start filling in the blanks, and probably one of the biggest challenges that faces us in archaeology is absence of data, and where we just don't have any information available. So as we build these models and we understand how different aspects of populations and where they live, how those things interact, we can start to have the potential to fill in the blanks. So I think there's valuable information that comes from both the qualitative and the quantitative models. The purely qualitative ones are often too loose or too complex and not sort of useful in a really sort of meaningful way. And then I think the quantitative ones go the other way. We often overfit with quantitative models. We don't necessarily know whether our parameter selection has been good or not. And they often fail to convey sort of the true nature of these relationships. The iterative simulations offer some limits to the model, but they don't tell us about parameter selection. So I think all of these things are contributing to these demographic truisms that I've been talking about, that keep popping up globally when we're looking at these big regional analyses. I think if we're going to escape these, we need more complex and more dynamic models that mean that parameters can change in scale, as they do in agent-based modeling, but that they can also change in weighting and hierarchy. And that's not to say that agent-based modeling can't accommodate that. It's just that it's not necessarily how it is used in all cases. So if we can come up with this sort of dynamic model that allows parameters to change in scale and weighting, then we don't necessarily use data to validate the model, because it's a dynamic model. The model's always moving. But rather we can explore how these variables interact under different conditions. And subsequently, this is how we may inform those gaps where we don't have data available. So the model that I'm proposing to do this, and at the moment, this is all sort of really preliminary stuff, but it's work that I'm kicking off now. So if you're interested, watch this space, is to use structural equation modeling to try and start accommodating more of this variability and diversity, allowing for this dynamic sort of model, and then using that to try and estimate data where data don't exist, essentially. So we can put in qualitative and quantitative, quantitatively accessible parameters, how they relate to one another. And we can also look at the hierarchy and the weighting of these, and how that might change and when that might change. We consider what parameters are vitally important, which are inconsequential, and anywhere in between, whether we can estimate them or not. Structural equation modeling allows for latent variables that can't be observed. So it's sort of a good tool, I think, in this space. And we can look at under what conditions all of these things change, whether the hierarchy of the parameters is changing, whether the scale of the parameters is changing. Feedback loops are obviously really, really important when we talk about population processes. And I honestly think within any sort of human processes, sociocultural or biological, feedback loops are really, really important. So we can accommodate all those things. We can have the creation of a database, which then informs the structural equation model. And probably my favorite thing about all of this is that outliers, or sort of things that are considered non-conforming cases, are accommodated and acknowledged in this sort of model. So rather than sort of going, okay, well, it doesn't look how we think it does, and either sitting it outside and trying to qualitatively explain why it sits outside, why it looks different, or just chucking out altogether, as is done in some of these sort of large studies. we can actually go, okay, we think that these are genuinely showing genuine variability and diversity in how populations respond. We can look at the conditions that's occurred within, and we can use that to inform the model. And structural equation models go through sort of continuous adjustments. And so we can have continuous adjustments for these things. It's not rigid. And then the model can sort of estimate the probability of a particular unmeasurable variable if we have enough measurable ones. So I suppose in cases where, and this is where the outliers are accommodated for, if we had, and I'm just using population data because it's my area, but this can be used for various things. If we have an absence of population data, there's no proxies to measure, but we know things about the environment, we know things about the belief system, we know about sociocultural interactions. We may be able to estimate the probability of a certain population process, so whether it's a high growth rate, whether it's a medium growth rate, whether it's low, but it is not necessarily a definitive answer. And I think that's a very positive thing. So we may say there's an 80% chance that population growth was high, but there's 20% chance that it was moderate. And that's driven by those outliers, so or non sort of conforming cases. They're accommodated, they're represented, and not treated as, you know, potential bias, I guess. So in the absence of complete data, we can examine the likely scenarios for population dynamics as well as other parameters. Structural equation modeling typically includes goodness of fit assessment, but it's not essential. We don't need to do this step necessarily. I think if we're sort of treating this as, you know, the benefits of it are that it's a dynamic model and that things move around, goodness of fit to me doesn't really make a lot of sense to include. So coming to the end, application of this sort of model in the Pacific. There's relatively little recent research into paleodemography compared on the global scale. And I guess in terms of the methodologies available, we have new methods available and they've been used pretty sparingly so far in the Pacific. For me, coming from the paleodemography background, for me, it's really exciting to be contributing demographic narratives that are outside of the Neolithic demographic transition, because this has really been such a strong focus. And I think it's quite problematic that it's been such a strong focus. You know, it's an area of interest, but why is it the sort of sole area of interest? Why do we see agriculture as this turning point in human civilization and human society? I think there's a lot of assumptions and biases in there. So any sort of research outside of that, I think, is a lot more exciting, and I think a positive way to sort of be looking at population processes, because it gets us away from this, you know, agriculture determines everything. The Pacific region has a high level of diversity. There's plenty of gaps in the archaeological record, but there's also plenty of data. We have these really great opportunities for comparison with other lines of evidence. Now, we don't necessarily need them to align. As I said, I think these sort of hopes of big population trends and everything aligns beautifully, I think, are just not representative of how these things operate. But I think it is nice to have these other lines of evidence to compare to. And I think the opportunity for these quite diverse case studies to be represented in a dynamic and complex model is a really great one. And I think due to the diversity and variability of the region, I think it's a really great opportunity to see the insights that we can gain from a model like this. I think the localized studies have just as much potential to contribute to our understanding of the scale and the impact of European depopulation in the Pacific as the sort of big regional studies that are typical of paleodemography at the moment. So I think there's really great opportunity there. So how do we operationalize this, or how am I planning to operationalize it? Definitely looking for collaborators in this space if anyone's interested. And I think we really need these multidisciplinary case studies of past communities, past populations, the the various events that impacted their lives, and looking at how different variables are interacting in different conditions. Through that, we can hopefully identify the parameters for inclusion in a model. So these interacting variables that are biological, that are sociocultural, and that are environmental in nature, not focusing, particularly on environment, giving plenty of weight to other interacting variables as well. And as we do this, we need to make sure that we're looking for things that are accessible in the past, or that it's a relationship that we don't expect would change significantly through time. So something like the relationship between sexually transmitted disease and subfertility. There's clinical research today. As a biological process, we would expect it to operate in a pretty similar manner in the past in terms of the relationship itself, not necessarily the scale, but just in terms of the relationship. So it sort of needs to fall into one category or the other. Either it's accessible, can be estimated, has a proxy in the past, or it's something that we think doesn't change much through time. In addition to case studies, we can meta-analyze some of the existing research on this. And as I mentioned before, we've got this opportunity for the continual adjustment of this sort of model, which I think is really nice. I think that flexibility is really fantastic and means that we can accommodate all of that diversity and variability without treating things as exceptions or outliers. That is me for today. Thank you so much for joining me, and happy to take any questions.
Thanks so much, Claire. That was really great.